Hello everybody, my name is Benoît Derain. I'm a machine learning engineer at Google's Advanced Solutions Lab. If you want to know more about what the Advanced Solutions Lab is, please follow the link below in the description box. There is lots of excitement currently around generative AI and new advancements, including new Vertex AI features such as GenAI Studio, Model Garden, GenAI API. Our objective in this short session is to give you a solid footing on some of the underlying concepts that make all the GenAI magic possible. Today I'll go over the code that's complementary to the encoder-decoder architecture overview course in the same series. We will see together how to build a poetry generator from scratch using the encoder-decoder architecture. You'll find the setup instructions in our GitHub repository. Okay, let's now have a look at the code. To access our lab, go in the ASL ML Immersion folder, then the Notebooks folder, then the Text Models folder, and in the Solutions folder, you'll find the Text Generation Notebook. That's the lab that we'll go over today. In this lab, we will implement a character-based text generator based on the encoder-decoder architecture. Character-based means that the tokens consumed and generated by the network are characters and not words. We will use plays as a dataset. They have a special structure, which are that of people talking with each other. And here you see an example of a piece of text that has been generated by the trained neural network. While the sentences are not necessarily making sense nor are grammatically correct, this is remarkable in many ways. First of all, remember it's character-based, so it means that it learns to predict only the most probable characters. Despite that, it was able to learn pretty well the notion of words, separated by blank spaces, and also the basic structure of a play with the characters talking to each other. Second of all, it's a very small network, as we will see. It's based on the RNN architecture and only trained for 30 epochs in the Vertex AI workbench, which is a pretty fast training time. So let's look at the code now. So the first thing is to import the libraries that we need. In particular, we will code our encoder-decoder architecture using TensorFlow keras. So we import that. Then we download our dataset using tf keras utils get file. So now the dataset is on disk, and we just need to load it into a variable called text. So the text variable now contains the whole string representing all the plays in that Shakespeare dataset. We can have a quick look at what it is, and you see if we print the first 250 characters, you have the first citizen speaking to everybody and everybody else speaking to the first citizen. This cell computes the number of unique characters that we have in that text dataset, and we see that we have 65 unique characters. Right? These characters will be the tokens that the neural network will consume during training and will generating during serving. So the first step here now is to vectorize the text. What do we mean by that? It means that, first of all, we will need to extract from the actual string a sequence of characters, which we can do with TensorFlow by using tf strings Unicode split. So now our example texts here are transformed into a list of sequences of characters. A neural network cannot consume immediately the characters. We need to transform that into numbers. So we need to simply map each of the characters to a given int. For that, we have the tf keras layer string lookup to which you just need to pass the list of your vocabulary, the 65 unique characters that we have in our corpus, and that will produce a layer that, when passed the characters, will produce corresponding ints. So within that layer, you have a mapping that has been generated between the characters and the ints. To get the inverse mapping, you use the same layer, string lookup, with the exact same vocabulary that you retrieve from the first layer by using getVocabulary, but you set that parameter to be true, invert equal true, and that it will compute the invert mapping, which is the mapping from int to cars. Right? And indeed, if you pass to this mapping sequence of IDs, it gives you back the corresponding characters using the mapping that's stored in the memory of this layer. So that's that. Okay, now let's build a data set that we will train our neural network with. For that, we are using the TF-Data dataset API, which has this nice method from tensor slices, which will convert that tensor of ints that represents our whole corpus of text, of plays, as int. It will store that into a TF-Data dataset. So at this point, the elements of this dataset are just the individual characters. So that's not great for us. What we want to feed our neural network with are sequences of the same length, but not just one character. We need to predict the next character. But luckily, the dataset API has this nice function batch that will do exactly that for us. So if we invoke the batch method on our ID dataset, to which we pass a given sequence length, which we set to be 100 here, now the elements, the data points that are stored in our dataset are no longer characters, but sequences of 100 characters. So here you see an example. If we take just one element, they are no longer characters, but sequences of 100 of their character IDs, if you want, not characters, but character IDs. Okay, it's not completely, we are not completely done here. We still need to create the input sequences that we were going to pass to the decoder, and also the sequences that we want to predict, right? And what are these sequences? They are just the sequences of the next character in the input sequence. So, for instance, here, if I have the sequence TensorFlow, the sequence TensorFlow at the beginning, then the input sequence we can do from it is TensorFlow without the W, and the target sequence that we want to predict is the same sequence but just shifted by one on the right, so TensorFlow. And you see that E is the next character following T, N is the next character following E, etc. So basically this little function does exactly that. It takes an original sequence, creates an input sequence from that by just truncating that sequence, removing the last character, and that just the target sequence is created by starting at the first character. So how we do that? We just map the split input target function to our sequence dataset. Okay, and that's our dataset. Now let's see how to build the model. First off, we set a number of variables, the vocabulary size, the size of the vectors we want to represent our characters with, right? That would be 256, and the number of neurons or recurrent layer we'll have. For the model itself, it's a relatively simple model. we create it by using the Keras subclassing API. We create just a new class called myModel, and we subclass here from TF Keras model. When you do that, you only have to override two functions, the constructor and the call function. So let's see what each of these functions does. The first function takes essentially the hyperparameters of your model, the vocabulary size, the embedding dimension, the number of number of neurons for your recurrent layer, and it just constructs the layers you will need and store them as variables of the class. Okay. Now, really, how these layers are connected, all that is specified in the call function, right? The architecture of your network, if you want. And let's see what it does here. It takes the input, which are sequences of ints representing the characters. We have a first layer that will create for each of the ints a vector representing that. So that's a trainable layer. So as the training progresses, these vectors representing the characters will start to be more and more meaningful. At least that's the idea. Then these static representations of the characters is passed to the recurrent layer that will somehow modify this representation according to the context of what has been seen previously, and generate a state of what has been seen previously that will be reused in the next step. Finally, we pass the output of the recurrent layer to a dense layer that will output as many numbers as we have in our vocabulary, which means one score for each of the possible 65 characters, and this score represents the probability of the character being the next one. So that's all that the model does. Then we instantiate it. Once we have done that, we can look at the structure of the model using model summary. And you see here you have the embedding layer, the recurrent layer, and the dense layer that we just encoded, implemented in our model. And that's that. So let's train the model. Before we train the model, we need a loss, and that's the loss function that will compare the output of the model with the truth, right? Since that's essentially a classification problem with many classes, and the classes being each of the possible characters to be the next, the loss will be the sparse categorical cross-entropy loss. And also, because the neural network output the logits and not directly the probability, we configure this loss to be computed not from the probability scores, but from the logit scores. Okay. Once we have the loss, we can compile our model, which means that basically we tie to it a loss and also an optimizer that will update the weights during training to decrease the loss as much as possible. Basically it. Then here we have a little bit of a callback that we will use and that will save the weights during training, which is useful. Right? And we are all set up now to start the training. So we do a model.fit on the data set. We choose a number of epochs we want to be trained on. An epoch is a full pass on the data set. So here we will have a look at 10 times the corpus of plays we have in our text vector. And we give the callback to make sure that the weights are saved during the training. That's it. So that's relatively simple. We train the model, we have a trained model. Now, what do we do with it? And that's a bit of a complication in the encoder-decoder architecture, is that you cannot really immediately use your model. You need to write a sort of a decoding function that's here, right, that will decode the generated text a step at a time using the trained model. Okay, so here in this case we chose to implement this decoding function as a Keras model. So we subclass from the TF Keras model. The main method in that model is the generate one step. Let's have a quick look to what it does. So it takes the input. So the input can be the prompt, the initial prompt, the initial sequence of character you want the encoder-decoder model to complete, to predict, to generate new characters. So we pass the input. It transforms that text into a sequence of characters, then this sequence of characters into a sequence of int using the ID from cars layer we have set up previously. And then we call our model, our encoder-decoder model that has been previously trained. And what does it do? It takes this input of int and output the predicted logits, so the scores for the most probable token, the most probable character in this case, along with a state that summarizes what has been seen previously. From the predicted logits, we can compute, we can select the most likely tokens or characters. But before doing that, here there is a little bit of a trick, which is that we divide the logits by a temperature, by a number. So basically, if the temperature is 1, nothing happens. But if the temperature is very high, what it will do, it will make that the scores associated to each of the tokens to be predicted next will be relatively similar, close to 0. This means that actually this token will be more and more likely to be chosen. Right? So there will be more variety, more stuff can be predicted if the temperature is high. So it's a bit more creative. If you have a too high temperature, of course, the neural network will just predict gibberish. Okay? And if you have a too low temperature, the highest probability score will be just multiplied by a very large number, because it's divided by a small number, a number between 0 and 1, which means that the highest score will be become much bigger than the other scores, giving a much higher chance to be selected, which gives you more of a deterministic behavior. Okay, that's the temperature. That's an important parameter in this type of architecture. Okay, and that's what it does. Okay, so now we have the predicted logits. We use TF random categorical that just sample from these probability scores the most likely IDs to be next. We transform that back to a character, and that's what we return. Okay, so that's essentially what the decoding function does. And most decoding functions have the very same structure. There is also this temperature trick that you can see as a parameters in the case of large language models. Okay, so let's use our decoding function. So typically you use that in a loop. So here we are going to predict 1000 characters by repeatedly making a call to the decoding function generated one step, to which you feed what has been predicted before, along with the state summarizing what happened before, and it predicts the next character along with a new state. And we start the process with a sort of a prompt here that's, Romeo, what are you going to say? And then the neural net, let's see what the neural net generates. Romeo, it says, no, good, Coriola, had leave take your fiddle, and if I seem to my love you. So you see, it's not, it doesn't make a lot of sense here. Remember, I've trained it only a few minutes on a workbench, AI workbench, Vertex AI workbench, which are great, by the way, but Here that's a small instance with just one GPU, so it was a very small training. The model is written in a few lines, but yet you still see that it can really pick up a lot of things in the structure of the input data. It detects as patterns that you have characters. So Romeo, that was our input, but then Leontes was generated by the network, and then what Leontes says also. Okay, that's it. If you like this presentation, you'll find more in our ASL GitHub repository with 90 plus machine learning notebooks. Don't forget, if you find it useful, please start a repo. Thanks for your time.